Alright, hell yeah. So we have another problem from the Pathfinder. And man, some of these problems I was just like, oh, I should be able to do this. And then I didn't. I just cried. I was like, damn it. So I couldn't do this one yesterday, so I'm just like, well, I don't even know what they were talking about. But it's just kind of interesting if you just think about it. Went on a bike ride and, and it was tonight that I was just like, oh, well, can't I just make this problem into, so this is going to be the strategy, is just, can you make a simpler problem? One is like, I didn't even know, okay, so what they're saying is, are these in equilibrium? Like, are they balanced? And like, sure, these things have mass, the pulleys have no friction, the string is massless, and all three of them are just going to chill out. And then it was just kind of interesting, like, what is the definition of stability? I think the definition, and let's look at this, because if we have an ideal spring and then no little hill, but we just have two masses, like what happens? What happens? So we have two masses that are identical, right? So what happens if we take this mass right there, and then just physically move these two masses to two different locations? Sorry, I didn't kind of line it up. This one should be a little bit lower. But if I just take these two masses, one up, one down, and then just hold them there, like this thing still should just be, not moving. So that kind of was like the first thing that came to mind, is just like, oh, okay. So if that's the case for this problem, is one of these where I move one up and one down gonna create a scenario? And I was just like, in my mind, like, what would be a scenario where, like, if you move the location of two different things, like one is hella, and what I thought was like, hey, let's say we have this mountain. It reminded me of, there's this book called Touching the Void. A guy gets injured, breaks a leg, and has to get lowered down the mountain. But all of a sudden, that mountain climber hits a cliff. And then how about, so, you know what I mean, and then nothing you could do. It's a crazy story. But anyway, so we're going to have this pulley up here. And so right here we're going to have a little person. Cool. And how do we draw a person? There we go, a little head. And then right here, kind of that same thing, we're going to draw a little person. And cool. And then we got, they're kind of harnessed up. But guess what? This person is about ready. We're going to just move this person to over this cliff. Well, get ready, because this person's going to be going flying up this mountain, and this person's going to be going flying down this hill. That would be an unstable equilibrium. You move the locations, and then all hell breaks loose. So that was kind of the interesting scenario. I was just like, oh, that makes sense. Oh, no. Let's continue on. So let's finish up this one. This one is C. And let's show, because if we move this ball, so it's steeper right here compared to up here. And so if we move this ball down here to the steeper location, right here, this person moves to actually a flatter location. So this is only representative of this moving to a steeper side. This side, heck yeah, like this person would actually come to a flat right there. That's kind of what I was trying to draw right here. So it's kind of opposite, but let's say this drops off a cliff, and then this comes to a flat spot. So this is also C, but just kind of flipped around, if you can see that. So now the question is like, well, what about this one? And this one's kind of interesting. I like that it has this kind of sloped path all the way down here. And let's bring this up to a total vertical. So we're going to take this ball all the way up to here on the vertical, and then this ball just on the flat. And let's say, just theoretically, this string is able to pull, for whatever reason, it's a magic string, and it's able to pull kind of in line with this ball. I mean, true to the problem, that's not the case either. When it's right here, it's still pulling at an angle. But I think you get it. So if this ball is right here, and then this is just on a flat, I was like, oh, hell yeah. That is totally like you have a pulley and you have a mass hanging. So here's your mass, and then you have another mass on a horizontal surface. Because in this case, if these two masses are the same and you have frictionless, like, hell yeah, you got some motion. Because sure, this has mass and it's got a force, but it's kind of balanced. And then this is the driving force. So this, you have the force of gravity, and this is hella unstable because it's going to be pulling that. So heck yeah. So same thing here. You have a driving force of gravity taking this to the center of the Earth, and you know what I mean? Even for these physics problems, they should be like, hey, this thing's on Earth. Like, I don't know. It's not at the International Space Station. I mean, I don't know. But, heck yeah. So that's why this will move, because it's just on a flat surface and you have all that driving force. Okay, so sweet. So that is going to be representative of B. And, but this one's cool because, this isn't technically representative of B. Because this is a runaway scenario. Like, the second this thing overtops the pulley, you know, the whole system's gone. Where the way we have it drawn right here, this thing is going to, you know, let's say it did just get a little bit out of sync. This thing might roll down to about here. It's kind of on the flat. This thing's going to roll up to about here. It's kind of on a slope. And so we're going to have a driving force down. It's going to pull this one back up. And then they're just going to switch spots. So heck yeah, this is spot 1 and 1. And then 2 and 2. You know, time 1 and 1. And then it's going to switch. And then these things are just going to oscillate back and forth. And so, so this is the one that is a stable balance point. Because we're going to, like, if we do shift it a little bit, heck yeah, this one's going to drive it down. But at some point, once this hits the flat, heck yeah, this is going to drive it back. You know, and then so it's just going to kind of hover. And, like, any slight that's the interesting thing. Because if they're talking, anytime they're talking frictionless surface, like, there's no such thing. And that's an ideal environment. So, I mean, but still, you should... If we do displace these, and they do have movement back and forth, they'll oscillate forever. But they will be balanced. Now, if you have a tiny amount of friction, and you do have some movement one way, well, heck yeah, they'll dampen out. But now this one, because this brings up... Alright, hell yeah. So this one is a runaway scenario. It just falls off a cliff, and then this just gets easier to pull up the flat. I mean, you know, like, obviously, once it... yeah, this one's going to get past the point of no return, and then we're just going to call that unstable. But now we need to figure out maybe why this one is neutral. And they don't have to be, you know, 1, 2, or 3 or anything. They can all be unstable. They can all be neutral. Or they can all be stable. But I wanted to tackle this problem for, hey, let's move them. Because that's what I was thinking. I was just like, what is the definition of stability? Because let's say I do have a little mass and we put it on top of a kind of a little mound, a little pyramid. And maybe we can get it to stay up there. But then what I was thinking is just like, oh, I think one of the definitions of instability is just like, well, can you move that mass just a little bit? So we're just going to move it just a little bit to the right. And I could have even just had it at the same elevation. But hell yeah, we're going to have an unstable... if we move it a little bit to the right or a little bit to the left, like, that thing's gone. You know, and it's a runaway scenario, so this would be unstable. Now, if we found a way to move it to the right and then move it to the left, and it could get back to its original position, that would be a stable position. So I was thinking, you know, if you had a pump track, you could balance at the bottom with your bike or at the top with your bike. And if you stopped at any of these 3 locations, these 2 are unbalanced and this one is balanced, because if we move the bike to here and just physically move it and then bring it to a stop, it might roll back. And it might have enough juice to roll back this way, and then it's basically going to get to that location due to conservation of energy, and it's going to oscillate back and forth. Now this one, if we're stopped and then we just kind of move just slightly to the right or slightly to the left, hell yeah, we have that runaway scenario. So this is an unstable balance point. Now, just because we have something, now in this case, my only criteria was if we just move the object and bring it to a stop. And this kind of brings up an interesting thing, because these are mass, and the only way to move a stationary mass that has 0 velocity is to put a force on it, and F equals ma, and then also, well, I mean, it should be obvious. We have to put a force on it, and then we're going to change, it is a mass, so we're going to have an acceleration. And the definition of acceleration is we're going to change its velocity over some period of time. And so just the fact that these would move at all, because in these problems, we get it. Maybe something just happens and it moves it. Well, the force must have caused that, and then we must have changed the velocities of these. So maybe this has now a velocity going that way in that direction, and this has a velocity going that way in that direction. Same thing with this neutral one. So if we come back to our pulley that's just like this, if this one just slowly starts to, if for whatever reason, Alright, heck yeah. If we find that this was the original, I'm getting phallic with it. Anyway, if we said that this was the original position, and then somehow this was now up here in a new location, well, the only way for that to happen is a change in velocity. At some point it had to have motion, even if it stopped, you know what I mean? But just the fact of changing position when the velocity is 0. I don't know, just for me, I just reiterate that all the time, because you're trying to find that initial condition. The only way to get this chunk of mass up there is to put a force on it and have it's a mass, and to have some sort of acceleration, which is a change in the velocity. Alright, so hell yeah. So that's why I'm going to say why this is a neutral, because the second that starts to move up, and this will move down, go back to everything. We have no friction. This is massless, this is massless. We just put 2 masses into motion. There's no other forces that, and the tension in this cable is going to be the same. Alright, heck yeah. So I guess the take-home point is, if this starts to shift, it'll just slowly, keep moving. If we induce a change in velocity, there's nothing to stop that change in velocity. There's no other contours to say oh, this hits a contoured wall, up here, that would work. Or this hits a contoured, if this one drops, it hits a trough right here, and the same could be on both of those. So if we had a scenario like this, where these are actually kind of captured in a half circle, well, hell yeah, that would be a very ideal balance point. Okay, so that is the only other thing. I think the neutral one is actually kind of the most confusing, because you're just well, if you put this into a location there and there, sure, I physically put them and then hold them and rest them. Well, they're not going to Alright, hell yeah. I had to take a long break on this and my mind is fried because all those scenarios that I went over is where the pulley is, where this rope is in line with the slope. You know what I mean? So the rope would have to be in line with this, and then you'd have a pulley right here. And I don't know if that's what they were intending. You know, because this one kind of plays out, you know, where the rope is fairly in line with the actual initial slope. But because in these two scenarios, the rope is not in line with the actual slope, this one's going to come up here, and then the pole is going to get steeper, and then this one's going to come over here, and then the pole is going to get shallower. And so I don't know. I think this one needs further analysis. So I did 2 drawings, and we're going to assess which one we're going to assess this one. So if this moves more vertical, so I did it to the extreme. So this one's going to move up to there, this one's going to move down to there. And same slope, you know, we have the same mountain. This one, you know, moved up to here, and you can see that this scenario, if we just place them there, not like move them with velocity, but just place them right there, you know, if it's an unstable balance point, it'll just keep going in the direction that we moved it. If we move it there, it'll keep going there. But look at this. We find that it looks like we just created this. Yeah, it's just fascinating because it looks like this is getting steeper, you know, farther away. And yeah, and that's the case, because this angle is what it is right here, but if this thing goes down here, this angle is going to go this way, where this one is going to go in. So I think they just drew this problem wrong. But now let's analyze C. This one is going to come up onto a shallow part right here, and it's going to come down on a steeper part. Well, sure, it comes onto a shallow, but same scenario as this thing. This thing is, the angle got swept out, and it still feels like this could have a potential to slide this way. Because now this thing is totally underneath and just taking full weight, where this isn't pulling down with full weight. So, yeah, hell yeah. So and they drew the problem where, I mean, they you know, they cut it right here, but still you could get that piece of mass right there, and you're more pulling in line. So I would say in this scenario, yeah, I almost want to set this up because this is really bizarre. So anyway, so my take-home conclusion is if you do this and then you put the pulley and then it's right in line, hell yeah. This is going to be a neutral position. You know, if you start to move them, neutral because it'll just keep going. And then, but neutral as in if you just physically move the locations, this won't, you know, it won't be a runaway. This one, man, should we try to draw that too? So we're going to do this. It's going to be in line. Put the pulley there, there. But now this one sweeps out. So when we move this one, we'll move this one up. And then this one slacks out to there. And then we have that classic case where it feels like this one's off a cliff and it's pulling it on a flat. So hell yeah. So this one, but this one is a stable balance point, because if we do that, and then this ball, so this is 1 and 1, but then this goes up to here at a time 2, and this come down here at time 2, this one will oscillate back and forth. But I think we kind of proved that because of this angle, man, these all might oscillate back and forth. So I'm just going to say, you know, well, I don't know what I'm kind of inconclusive. That's why this is probably such a good video. And then same thing on this one. I think it was intended. So we're going to have the pulley, you know, I mean, it's going to be in this position, in this position. This one comes up here, and then this one starts to, you know, slide down. And so this one's still in line on a, but much on a much flatter surface. You know, I think let's redo this one like I think they wanted it. And I think we can do a good job of showing kind of what they were after. So we're going to do this. Yeah, that looks pretty good. And now we want something to be able, like the rope should just be able to, you know, go up and over this pulley. Same thing here. We're going to make it so, heck yeah. So there's maybe the final locations, but the initial locations are going to be right here. The rope's going to be in that location. Right here, the rope's going to be in that location. If this one goes down to here, this one, and I wish I made this more flat on top, but we're just going to have it right here. I guess just pretend that it is fairly flat on top. Yeah, as long as this rope doesn't get in the way, we could have a total flat top right there. So at some point this is going to roll up to a flat, and then at some point this one's going to be steep. So that's the scenario where you have a pulley off a cliff. So I would say check on the instability of this one. Yep. So I think this is how they wanted it drawn, where you for sure would have an instability. But the way they have it drawn is that now this one comes totally underneath and is being pulled up vertical, where in my scenario this hits a flat spot on top and it very much mimics this. So I think the way they have this drawn, I don't think it was very well thought out, where you would really have to analyze the angles and the angle of this and how that changes, and just to see if it is unstable. And we're talking degrees, man. You know what I mean? If they don't have this within degrees, yeah, maybe it is. Maybe you can oscillate it back and forth, or maybe it is like this and it's a runaway. So anyway, so cool. I think I'm done with this video, and definitely will explore it more. But I thought this was just going to be a 2-minute video, but it's so cool where you can kind of split hairs and be like, nah. But we gained a lot more knowledge than just the way I thought it was done. Anyway, so thanks for joining me on this one, and that's a video.